It's time to start our first panel of the SH session. We have several talks, and the first talk is time-dependent propagation, times and energy losses of protons in the heliosphere, and the talk will be given by Rose Calais. You have the floor.
Thank you. I think if I put here, oh no. Okay. Good afternoon, everyone. I'm Berlusconi from Italian Space Agency, and I'm going to talk about the protons propagation time and energy losses evolution inside the heliosphere by using a model, numerical model, and the solar modulation modeling with the observational cosmic ray observational data. As we know, the galactic cosmic rays mainly are originated from the galactic sources like a supernova remnant, and Voyagers reported and also they measured the fluxes for the protons, for instance, outside the heliosphere, and some experiments like AMS and Pamela, they measured inside the heliosphere close to the Earth, the intensity and the fluxes of the cosmic rays like proton. And we know once the cosmic rays enter the heliosphere, they interact with the magnetic field and also the solar winds. This interaction will cause some significant global and temporal variation in their intensity as a function of the space and time and in their energy. So the intensity will change. This called the solar modulation. As we see here in this plot, shows the four local interstellar spectra from the Voyagers and also for the AMS for both proton and helium. We see in the lower region of the energy, we see some gap, could be sign of the solar modulation. Okay, space experiments like AMS and Pamela both covers, if you see here, from 2007 to 2017, covers all the cycle, the solar cycle 24 and part of the solar cycle 23, and also the maximum solar activity and minimum solar activity, and covers the reversal phase, for magnetic reversal phase, and for both polarity and also both negative and positive polarity of the magnetic field. So we have enough data, Voyagers, AMS, and Pamela. And the good news is the AMS and Pamela reported the fluxes for the proton as a function of time, in the time units of monthly in a Barter rotation for each Barter rotation. The best way to study the cosmic ray propagation is Parker evolution equation. And in this study, we use the solar prop, a numerical approach, numerical integration in the steady state. And as we see here, when the cosmic rays come here, but with the backward time integration based, we see, for example, when one cosmic rays came inside the heliosphere and close to the Earth, here we call it initial energy, here we call it final energy. So for us, from now on, because without backward time integration, just for to apply in the solar prop tool. Okay, in this propagation model, we have used the calculation for the Parker equation. It's not calibrated. Okay. Parker equation for cosmic ray density and also the stochastic method. Our key data are Voyager, as I told, Voyager, and also the AMS and Pamela. Voyager provide the cosmic ray from outside the heliosphere, and AMS and Pamela, the monthly variation cosmic ray fluxes inside. The key ingredient and also the key parameters in this study are rigidity, the diffusion coefficient is which is a function of the time and rigidity. We see in this figure in this here how the dependency of the how it depends on the rigidity has different behavior below and above 3 GeV, and for each regime we see is a power law K0 rigidity and A and B. So these three parameters which are time dependent K0 and the indices A and B, as well as the parameters describe the heliosphere like magnetic field, heliospheric magnetic field, the solar winds, and etc., make the parameters for our model. So finally, 6 parameters: tilt angle, magnetic field, heliospheric magnetic field, polarity, which these parameters can be defined for given approach by some solar observatories, and the other trees that I introduced here can be found by the fitting with the data, the observed data. Okay, so this is the whole story and the path we went through this model. Just using some typical values to see how this code and model works. In 2 different polarities, positive and negative polarity, we used this model, and you see here when particles, a single proton, when enters to the heliosphere, enters from the in the positive polarity, came from from the poles, and you see here the histogram. You see from 0, and mainly came from the polar region. However, in the negative polarity, we see here almost this is the for single trajectory for single particle are from the heliospheric current sheet. So in these 2 different regimes, polarities, how propagation times, how we can compare them. In the negative one, in the negative polarity, we see here are longer, the propagation time is higher and is longer compared to the positive one, which is shorter. Consequently, their energy loss also we expect is higher. So they lost their energy higher comparing to the positive energy. So this is consistent with the general drift consideration. For the negative cycle, protons reach the Earth, and so they take much longer time to reach to Earth comparing to the protons simply drift towards the Earth from the polar region in the positive cycle. Okay, so now we apply the AMS and Pamela data to this model in order to find the best parameters for the diffusion coefficient for each mount from 2007 to 2017, the life cycle of the Pamela and the AMS that we have data in this region and we publish data. Okay. So here, fitted the model with we see for the selected epoch for both Pamela and AMS data, which are fitted well with the model here. So by fitting these 2, we can find those parameters. One of the co-authors of this work, Fiandrini et al., recently published, and with the more details, I would refer to this paper just to see the more details and find out how they found it. So here are our 3 parameters, and other 3 parameters came from the observations: tilt angle, magnetic field, and polarities here. How it evolved in the time. These 3 came from the solar solar observations. But these 3 that I told you, the K0, A, and B indices, for each mount from 2005 to 2017, which covers the AMS and Pamela, we can find for each mount these values. So we can find propagation time in each time unit. Okay, here I show our results just for two energies. The 1 GeV means the energy of the protons close to the Earth. Okay, those protons came to the close to the Earth. How they propagate after entering to the heliosphere. So the propagation time, this is the evolution of the propagation time, and this is the sunspot numbers. We see is correlated to this, so the same behavior as the sunspot number. And also we expect the same because the energy losses have the same behavior for this energy. Okay, I put also here a bit higher energy, 4 GeV, the protons close to the Earth with the 4 GeV. We see is a bit flatter. And I didn't put here, but we tested for the higher energy, let's say 10 GeV, 20 GeV, we see almost flat. So the solar modulation effect vanished for higher energies here. Okay, now, okay, we found this kind of modeling using the AMS and Pamela. But in order to cover more solar cycles, we applied the BESS and SOHO data, but not monthly, they are not monthly, just to back to 90s and to cover more solar cycles, just to see and how they evolve the propagation time, but by those data. Again, these are the three parameters, and the other parameters we found by fitting with those data. And of course, the Pamela and AMS here. Again, the propagation time for protons with the energy 1 GeV back to 90s, and also the solar sunspot number here. The energy loss as well by extension to the 90s. And here this figure shows the propagation time versus kinetic energy in 4 different regimes. Which regimes? Solar activities, minimum and maximum solar activities, and also in each region with different opposite polarities, positive and so totally we have 4, and these are selected time approach with these conditions. We see here the longer propagation time happened when we are in the solar maximum, yes, in the negative polarity, and also the shorter propagation time happened when it's solar minimum positive polarity. And the energy losses here, as we expected, you see here the energy loss is higher than we see 2 regimes, 2 is divided. So green and the black are for the solar maximum, which are higher than these data points in the solar minimum, which is reasonable because in solar maximum we have turbulent magnetic field and lots of irregularities, and so consequently we have lots of proton interaction, so they lost their energy during the solar maximum activity. Okay, so to my conclusion, we used the stochastic model to simulate particle trajectory, and we found particle trajectory. We modified this one as a function of time also for time steps, and the model, the parameters of the cosmic ray diffusion is tuned to the observation time dependent cosmic fluxes, and we use the AMS Pamela BESS to cover the more solar cycles. The other physical inputs, which came from the solar physics and solar observatories, we are looking at particle trajectories, propagation time of cosmic rays, and their energy loss using our model globally tuned over a larger time interval. And finally, the evolution of cosmic ray propagation time and their energy losses are correlated with the solar activities. Okay, thank you.